the lower second. So for this case, they tell us buckling will not occur in IYY. Buckling will occur in IXX. Okay, so that statement is important. So over here, what they want us to determine is the maximum deflection. So we have to find what is our Y max, and we have to determine the maximum stress. Okay, we have to determine our maximum stress. And we know these are all based on eccentric buckling analysis. So there's two formulas that we are going to use. Okay. So again, you don't need to memorize all this formula. There's no way I could memorize this formula also. So we are going to find, so this formula will be provided is equal to P over A, okay, bracket 1 plus by EC over R squared, okay, and then will be secant pi over 2, and then we have P over PCR, okay. And again, we know that, note that PCR is equal to pi squared EI over LE squared. Okay. Well, let me write this properly. Okay, so I'm going to put in square brackets indicating to you that these formulas will be provided. So this one will be provided. I don't need you to memorize this. And this will also be provided. You don't need to memorize those. Okay. And we also, so the question also asks us to determine Y max. So Y max is equal to E secant, right? Bracket square root P over EI. And then we have L over 2. And then if I'm not wrong, so the secant is over here, and then minus 1. Okay, let me check the formula. Oh, I am missing a square bracket. Beg your pardon. Okay. Again, this formula will be provided in your term test and also your exam. Okay. So now we have all this. Okay, I'm going to bring the figure down. We draw our transformation. So we have to be careful over here, because we have to follow the transformation like in this diagram over here. We have to follow the transformation in this diagram over here. Okay. We have to follow the transformation in this diagram. So that is the cross section. Okay. So this is the cross section. Right, cross section. So if we look at that view, this will be our Y. Okay. And then coming towards us, a dot will be our X. Okay. So I'm trying to do this in, if this is Y, this is X. So going up, okay, X to Y. So going up using the right hand rule, this is our Z. Okay. So this over here is our rotation about X. Yes, that's our rotation about X. So as mentioned, right, as mentioned, buckling will only occur in the x-axis, or about the x-axis. Okay. So what it actually means, okay, I'm going to sketch the deformation. I'm going to sketch the deformation. Okay, the deformation will look, hold on, the deformation will look like this. Okay, so this is our deformation pattern. Wrong color, sorry. So this is our deformation pattern. Okay, so this is our deformation pattern. Over here, this is our deformation pattern. So you look at the curvature, right? If we were to look at the curvature, right? The curvature is like this. And if I were to draw Rx, right, in this way, right, the curvature is the same. So it's going to rotate about the IXX direction. Okay. So the first thing we have to do now, so before I go on, have I mentioned enough yet? Okay. So we are okay. So you'll be asking me, Eugene, why we have to determine IXX. Okay, so before I go on, we have why determine IXX. Okay, we need to determine IXX is because IXX is equal to A radius direction about x-axis squared. Okay, only if we know our Rx squared, right? Only if we know our Rx squared, this term over here, or our Rx, right? Then we can know what to put in for our R over there. Okay, so that's why we need our Rx. Okay, so we can start doing that. So focusing on the diagram, the cross section, right? XX, so this will be our width, right? Over here, this over here will be our depth. Okay, so what I'm going to do to find the second moment of area is I'm going to do this. Okay, so I'm going to sketch our cross section. I'm going to sketch our cross section out in here. So this is our cross section. Okay. So what I'm going to do is I'm going to take the whole square. Okay, so this is the axis of interest, XX. Okay, XX. And then I'm going to minus this region. Okay, I'm going to show you two ways of getting your IXX. So this is one way I'm going to do. Okay, so from here we know that this IXX is what we declare. This will be our width, and this direction over here, this will be our depth. So IXX is equal to, so the width is 100. Our depth, so it's 10, 10, so 120. About 3 divided by 12 minus. Okay, so the shaded region, there are 2. You multiply by 2. Okay, and then the width is what? Let me see. The width is 45. The depth is 100. power 3, and then we divide by 12. Okay. So from here, this will be equal to 100. 120 power 3 divided by 12 is equal to 14.4 times 10 to the power 6 minus 45 times 100 power 3 divided by 12 times 2 is 7.5 times 10 to the power 6. So this will be equal to 14.4 minus 7.5 is equal to 6.9 times 10 to the power 6 millimeter 4, or 6.9 times 10 to the power minus 6. Now you can use this method, or another method that I'm going to show you, or okay, since we are here now, later on when we do bending moment, you know what to do. So I'm going to, or the next approach is I'm not going to remove anything. Okay. But rather, so this is our ZZXX, I beg your pardon. I'm going to divide this into 3 parts. Okay. So I'm going to divide this. This is number 1, number 2, and number 3. Okay. So now the formula for the second moment of area ran out of space. I'll copy and do over the next page. Okay. So I call them 1, 2, 3. Okay. So IZZ1, sorry, IXX1 is equal to, before I write IXX, I'm going to write IXX is equal to width depth cube over 12 plus by area. So it will be big Y bar minus small y bar and the whole thing squared. So this is the general formula. Okay. We did not need to minus in the previous one because the entire section centroid. Okay, if you look at this one, you realize that we don't have the area minus by big Y bar, small y bar, because the individual centroid. Okay, so let's look at this shaded region. Okay, let's look at this shaded region. The centroid for the shaded region, okay, is exactly on x-axis. So that's why the big Y bar minus small y bar is equal to 0. And then if we were to look at the outer perimeter, right? We look at the outer perimeter over here. Again, the centroid is at the same place. Okay, so that's why you no need to minus the a bracket big Y bar minus small y squared. Okay, you don't need to do that. Right. So over here, we need now. Okay, so so we need it for IXX1 and 2. We don't need for 3. Okay, so we're going to write IXX1 is equal to IXX2. So the width is equal to 10. Wait. So this is the, sorry, this is the width. It's so important to do this. This is the depth. I can get it wrong also. So the width is 100. The depth is 10 cubed over 12 plus by the area 100 multiplied by 10, then multiply by so the centroid is at where? So it's at 120 divided by 2 minus by 10 divided by 2. Okay. So why did I do that? Okay, why did I do that? Just to recall. So if I take the datum over here, right? The distance from here to here by observation, the centroid is equal to 120 divided by 2, right? And then if I take the section 1 or 2 centroid, it's exactly over here, right? And this distance from here to here, this is equal to 10 divided by 2. So that is why it's 120 divided by 2. So at the end of the day, what we are trying to determine